Good morning to one and all. I welcome you all for the today's session, morning session. Okay, I'm Raju Patil, from Mechanical Department, Angli Engineering College, Belagavi. So I will be today dealing with continuous chips. Okay, a continuous chips is a ribbon type chip which is produced during cutting of ductile materials such as low carbon steel, copper, brass, and aluminum alloy. Okay, the material is subjected to both compression and shear. The chip slides over the tool rake face for the some distance and then leaves the tool. You all can see here the space between chip and the tool. Okay, the chip slides over the tool rake face for some distance and then leaves the tool. Okay, friction between the chip and the tool may produce deformation of the chip material called secondary deformation. In sketch you all can see the secondary deformation and primary deformation. Okay, and you all can compare what is primary deformation and secondary deformation. Okay, so heat is generated in two deformation zones. Heat is also generated due to sliding of chip on the rake face. The heat generated results in the increase of temperature of tool chip interface and the tool and that of tool. Okay, rake angle of tool. The size of the primary zone of deformation depends upon the following factors: rake angle of tool, cutting speed, properties of work material, friction on rake face. What is rake angle? The transition of work material into chip is gradual and the material suffers less overall deformation if rake angle of tool is large. The cutting forces are small if the rake angle is small or negative. The material suffers more severe deformation. The cutting forces are also large. The cutting speed. The thickness of primary zone of deformation reduces and zone becomes narrower with the increase of cutting speed. Work material. The size of the primary of zone depends upon the following properties of work, that is, first one strength, second strain hardening, third strain rate, and fourth is heat conductivity. Okay, and fourth one, that is friction on the rake face. The size of the both primary as well as the secondary zones of deformation increases due to increase in friction between the chip and the tool rake face. And in figure you all can see the when chip and the chip and the tool rubs each other, the friction between the chip and the tool rake face occurs. Okay, continuous. Next one we are going to deal with continuous chip with built-up edge. You all can see the chip and the tool, and you all can see the see in the figure the fragment of BUE. BUE is nothing but built-up edge. Okay, and you all can see the arrow mark shown in the figure where is the built-up edge formed between that chip and where the chip and the tool meets at their edges, above little bit from the edges, built-up edge is formed. Okay, the chip slides under heavy pressure on the rake face. Also there is high temperature between the chip and the tool. Due to high temperature and pressure existing, the chip may stick to the rake face of the tool. The heat of the chip is conducted to the tool at close contact area. The chip becomes stronger and more of the deforming work material is attracted. The size of the built-up edge goes on increasing till a critical size. When it reaches to the critical size, it breaks. The broken portion of the built-up edge gets embedded into machined surface or gets attached to the underside of the flowing chip. The building up and breaking of built-up edge is cyclic and there is a regular embedding of broken built-up edge into machine surface. the surface friction is affected due to this. With the increase of cutting speed, the temperature of cutting zone increases. The built-up edge is softened at high temperature and critical size of built-up edge reduces. Thus the built-up edge reduces. At very high cutting speed, built-up edge disappears completely. Next one, discontinuous chip. You can see in the figure, you can compare till now all types of chips you have observed. So what is the difference between by comparing all those, you can confirm what is how the discontinuous chips occurs. Discontinuous chips you can see in the figure, chips are of different shape and size, okay, and those are fully attached or beside the tool, okay. Discontinuous chips are produced during the machining of brittle materials such as cast iron and brasses. There is a crack formation in the deforming zone ahead of cutting edge. The crack travels with further advancement of tool and results in the formation of small lumps of chips. These are the lumps of chips. You all can see the lumps start moving up the rake face. Okay, the friction force obstructs the motion of the lump and crack propagates towards the surface. The fragment of chip gets detached. The energy generated in the cutting zone is mostly carried by the chip and tool life increases due to its lower temperature. Next we will be dealing with segmented chip. During machining of most engineering materials, segmented chips are produced, which are the combination of continuous chips and discontinuous chips. The shape of this chip depends upon the rake angle, cutting speed and material properties. These are the three factors, main factors. Orthogonal cutting. In orthogonal cutting, you all can see the cutting edge of the tool is perpendicular to the direction of the cutting speed. You all can see the chip which is in a box shape. And next, shear plane. The work material deforms plastically ahead of cutting tool edge. It slides on the rake face of tool and forms a chip. The region between the start of the chip and undeformed workpiece is called the zone of plastic deformation. Okay. Shear plane angle. The angle between the cutting velocity and vector and shear plane is called the angle of shear plane. That is phi. The chip is formed by plastic deformation of the work material and the material flow is continuous. Okay, but here material flow is continuous. You can see the equation of continuity. TBV is equal to T suffix C, V suffix C and V suffix C, where T is depth of the cut, B is width of the cut and V is cutting velocity, and T suffix C is chip thickness, T suffix C is width of chip and V suffix C is chip velocity. In most cutting processes, B is equal to B suffix C. Therefore, TV is equal to T suffix C into V suffix C. The chip thickness ratio R suffix T is equal to T by T suffix C is equal to V suffix C by V is equal to L suffix C by L, where L is uncut chip length and L suffix C is length of the chip form. From this figure you all can confirm that AC, you all can see it is mentioned alphabetically. AC is equal to T by sin pi is equal to T suffix C by cos into pi minus alpha. Okay. Fundamentals of machining and materials, you all can refer this, where alpha is equal to rake angle of tool and R suffix T is equal to T by T suffix C is equal to sin pi divided by cos into pi minus alpha. So therefore tan pi is equal to R1 cos alpha divided by 1 minus R1 sin alpha. And what this? The shear angle of the experimental found out from R1 and rake angle alpha. A pipe of ductile material is turned with the help of tool with the side rake angle. Into bracket you all can see the condition for orthogonal cutting. Measure L and L suffix C and calculate R suffix C. Measure the rake angle alpha. The tool should have only back rake angle and side rake angle, side zero rake angle for orthogonal cutting. Okay. Well, we can solve one problem on this. The end of the pipe was orthogonally cut with a tool of 20-degree rake angle. The chip length was measured as 85 mm, whereas uncut chip length was 202 mm. Determine shear plane angle and chip thickness if depth of cut was 0.5 mm. Assume the chip width B suffix C is equal to width of uncut chip. Okay. Chip length L suffix C is 85 mm. It is given. Okay, in a given data. Length of the uncut chip length L is equal to 202 mm. Chip thickness ratio R suffix D is equal to L suffix C by L. That is 85 by 202. That is 0.42. Tan phi is equal to R1 cos alpha divided by 1 minus R1 sin alpha. If that is equal to 0.42 into cos 20 degree 1 divided by 1 minus 0.42 sin 20 degree. Shear plane angle pi, that is equal to 27.4 degree. Chip thickness T suffix C, that is equal to T by R suffix T, that is equal to 0.5 divided by 0.42, that is 1.1 mm. Okay, with this we end up